Hello, this is Jeffrey Fox, the instructor of Big Data Applications and Analytics. And we're doing the data science curriculum of the School of Informatics and Computing. And this is lesson 14 of Unit 2, the course motivation. And it describes software ecosystems. And in particular, discusses parallel computing and MapReduce, but actually has a somewhat more general focus than that. Here we see a beautiful mosaic of various cloud things from companies and capabilities, services. Here we have NoSQL databases, management and monitoring, Hadoop, and so on, and various analytics and so on. And open source, we have Spark, Hadoop, Yarn, what have you. Just the richness of the cloud world is illustrated in an amazing fashion. And lots of this stuff are software, not all of it, but they're all use software and put together in different ways to provide services. So we can look at this in a slightly more modest. All right, here we have 350 software packages. This was probably originally about 40, done by me and Supin and Judy Chu when we were collaborating together in the beginning of inventing what we call HPC ABDS, the High Performance Computing Enhanced Apache Big Data Stack. And this has 21 layers. It's numbered up to 17, but there's some A's and B's, so it's actually 21 distinct layers. And they just cover some cross-cutting things like security, coordination, protocols, and monitoring. And then we have from the bottom up, we have all these interesting things: infrastructure as a service, DevOps, interoperability, file systems, resource management, data transfer, file management, NoSQL, SQL or NewSQL. Notice these are all part of 11. We start off with file management, which is actually pretty traditional in the science area, and where IROS is part of the best known system. And then we have the more common commercial NoSQL and SQL systems. We have extraction tools. These are sort of tools, level 12. Object relational MapReduce, in-memory caching. Here we have inter-process communication collected, RabbitMQ, ActiveMQ, ZeroMQ, Amazon Lambda, Google PubSub, ZeroQ. Lambda is probably better put up as a programming model. I think we classify it today. It's based, it needs inter-process communication, but it's more an event-driven programming model. But anyway, we have programming models, streaming, and batch. We have the high-level systems like Hive, which builds on Hadoop, or Shark that builds on Spark for those cases offering SQL capabilities. Dremel, as we mentioned, is the same as Apache Drill, which we have here, and which is sort of, again, this way of mapping, automatically querying unstructured data. Application hosting frameworks like Google App Engine, and there are all sorts of interesting systems here, which are sophisticated, high-level platform as a service. Then we have the growing number of application analytics engines. The most recent ones are TensorFlow from Google and CNTK from Microsoft. And at the top, we have orchestration or workflow, where BPEL was a famous community standard. Aerovata comes from Indiana. Pegasus, Kepler, Swift, Taverna, major HPC system. And Uzi, Naiad, sort of more, Flume Java from Google, and Crunch are the more Apache systems, or I should say more big data systems. So NiFi is actually a pretty interesting, from the National Security Agency, a pretty interesting orchestration system. So that's this is I should point out that this is January 29, 2016. It's I stopped updating it. There were so many packages here, it doesn't seem any point in continuing to update them anyway. It wouldn't fit on the page probably. So that's where we stopped. Thank you very much. We have lots of talks and papers expanding on this kaleidoscope.
All right, here we celebrate Google's contribution to building the big data stack. Although actually there are many Apache analogs of Google technologies, but Google usually keeps its technology to itself, but publishes brilliant papers which tell people how to copy them. This starts off, and here's a plot that Google likes to present. It's not such a great resolution because it's copied from a video. And this starts in 2002 with the Google file system, which becomes the Hadoop file system in the Apache stack. Then we have Apache Hadoop corresponding to Google MapReduce, Bigtable, which is Apache HBase, Dremel, which is Apache Drill, which allows you to do effectively SQL-like queries on non-SQL data, Prego, which is the equivalent of Apache Giraffe for processing graphs, Flume Java, which is an early orchestration technology, Apache Crunch. It becomes Apache Beam, which is over here, Google Cloud Data Flow. Colossus is an even better Google file system. Spanner is a so-called NewSQL database because people found that NoSQL had some problems because it was too unstructured and was for the Marine Corps worked well, but for real people was not so good. Another database F1. Millwheel is Google's version of Apache Storm and Heron. Twitter Heron, that's now Apache Heron. It's a successor to Storm. A Beam it actually runs with Spark or Flink or even our own Twister 2 system, and it implements cloud data flow orchestration. Now, there are some areas of great importance where Google hasn't written the seminal paper: security, data transfer, scheduling. Although Kubernetes is pretty important in scheduling, I should probably have put that down. Let's say we should do that. Kubernetes, that's a Google technology, which I didn't put down. Actually, it's not in that plot, is it? They should add Kubernetes to that plot. Serverless computing, I mean, Google Engine supports serverless computing, but they didn't have the early dominant software. Actually, it first came, I think, from Amazon, although OpenWhisk, which is Apache serverless, comes from IBM. So they're all, I put in here these layers where 17 is the highest layer, the orchestration layer. So Google has done lots of wonderful things for software, except to say it's all inside them because they offer the world's greatest services. I don't want to tell people their innermost secrets, just their outermost secrets. All right, thank you.
So of course you don't actually need 266 because there's some duplication, and if you focus on a particular area, you don't need everything. And here is some selection with monitoring. We do Inca, Ganglia, Nagios. Infrastructure as a service, we have Amazon Azure, OpenStack, libcloud, the library. Cloud Mesh is our own DevOps tool, but the more important public tools, Chef, Puppet, Docker, Cobbler. I mentioned these file systems already and these cluster management systems. Zookeeper is a critical coordination technology used, for instance, in Storm. Data management, here the NoSQL databases, and here we have SQL. In memory, we've already pointed out that's very important. Gartner's already highlighted that. Parallel programming, we have Hadoop and Spark and things at the low level, Storm for streaming. High level of Hive, which is SQL on HBase and Hadoop, and Pig, which is a higher level version of Hadoop, and then, or MapReduce, I should say. Then we have data analytics, Mahout library in Apache, R, famous library, ImageJ in image processing, Scalar back in HPC. Workflow, we have some class, we have Python as a sort of classic language-based workflow. Pegasus and Kepler HPC systems. In Apache, we have Tears, Crunch, things like Flume Java and so on as classic as coming from Apache. Apache is likely to have a major impact on the workflow environment, in my opinion. But it hasn't quite happened yet because Apache is only just producing tools in this area. All right, now let's get back to parallel computing. And actually, this is a review of things I already said. We have high performance computing, lots of supports low latency messages, tends to use message parsing interfaces. The technology runs runs jobs with lots and lots of cores, 100,000, a million cores, and all these facilities run at 100% utilization in batch mode, so you have to wait a while to get your results back. They tend to be fault fragile because they run in very robust data centers, but the software ecosystem does not tolerate faults very well. Okay, so then we have MapReduce, which has asynchronous maps. It's just pointed out here that the one feature of MapReduce is very tolerant of some outlier jobs taking longer than others. HPC is totally intolerant of that because if one node holds up all the other nodes and the other nodes fall idle, and then you have a huge cost. In MapReduce, where things are written to disk, you don't see that problem. So MapReduce is actually much more tolerant of not only hardware problems, but also software and load balancing issues. And there's the very important map-only special case, which is pleasingly parallel. We then pointed out that iterative MapReduce fell between those two limits. They take MapReduce and cache results in between steps. And they support the same single program, multiple data. That's what it says up here. Programming model, which you use in parallel kernels like linear algebra, clustering, and other data mining examples. So we have a relatively clear situation with clouds and HPC and technologies which are in between. Here is a nice picture of MapReduce. We have instruments producing data going to disks. Those disks are then supported by computers. So here we have the computers doing the maps, mapping the data. We have one set of maps, then we do a reduce phase, another set of maps, reduce phase, another set of maps, a big reduce phase, and then the final reduction phase before you get the answer to the users who make then decisions. Here we have DIKW, data, information, knowledge, wisdom, and the final decisions being made here at the portal. So the next slide you need to just look at. It's done by Salia and Judy Chu, and it uses converting an apple into juice as an example of a map. This is a map. And that map, of course, in this case is done by a knife, which cuts, and then a blender. It actually has two steps, two maps. Knife, cut up the apple, that's this, and then a blender to take the apple slices and make the juice. So this is sequential. One apple runs through the process. Then we could try to do parallel computing for this, and here we show a nice picture of parallel computing for doing juice production, starting with a collection of data sets. These are the initial data sets over here, which are mixtures of 3 fruits. And those fruits are the keys, and then the values of the initial apples and the slices of the apples. And then you get at the end this bottled juice. So this is an illustration of how MapReduce works. Here you have the maps. you have the reductions as you join all the either pure juices or mixed juice in the particular ratios. And this mapping and how it's implemented is sort of meant to illustrate in a qualitative fashion some of the key ideas of MapReduce. So, thank you very much. That's the end of lesson 14.